So, greetings, students. So, in this lecture, we'll be dealing with your uh, main principle involving your induction motor. Okay, so at what principle your induction motor is operating, we'll be seeing in this lecture. Okay, so the main principle involved in your induction motor is that it is nothing but your rotating magnetic field. Okay, the same rotating magnetic field concept is what we have seen more or less with your this will be more or less similar to that of the working of your transformer. Okay, so in your transformer what happens is that so you'll be having a core. Okay, so here you'll be giving the supply V1, so here you'll be having a back EMF E1. Okay, so here current will be flowing I1, so this is your primary side. Okay, primary side, and again at the secondary side you'll be having E2. Okay, then I2, and then after that you'll be having here your load. So load, which is nothing but your V2. So this is what your secondary side. So similar to that, this primary side will be more or less similar to that of your stator in your induction motor, stator of your induction motor, and this secondary side will be more or less similar to that of your rotor of your induction motor. But here in a transformer, both your primary and secondary are stationary. Okay, both your primary and secondary are stationary, whereas in your induction motor, both your your stator is stationary, whereas your rotor is a rotating part. Okay, so that's the main difference. So due to this rotating part, you'll be getting a rotating magnetic field. So here, due to the induction in the transformer, due to the induction of the magnetic field in your primary, due to mutual induction, you will be getting a secondary magnetic field in your secondary side. So these two are nothing but a primary, what you can say, stationary concepts. Whereas if you are coming to your induction motor, induction machine, you will be having one as a stationary and other will be as a rotating. So what they are saying is that the balanced three-phase winding is mechanically displaced by 120 degrees. So now, again, I'm saying we have been talking about three-phase windings. Okay, so hence for a balanced system, your ROV will be 120-degree apart. Okay, so here rotating magnetic field, that is you are inducing this three-phase supply to your stator. Your stator you are supplying. Then a rotating magnetic field at a constant magnitude of speed is produced. Okay, so that speed is given by the formula n synchronous. Okay, so this is will be calling as a synchronous speed. Okay, synchronous speed they'll be calling, and p is the number of poles. So this is what your poles looks like. Okay, so pole will be talking in terms of pair. So this is a, so this red color and red color is one pair, blue color and blue one is one pair, and this black and black is one pair. So here it is a three pole system. Okay, so it is a three pole. So there will be generation of pole pairs. Okay, so here based upon this you'll be having, as I said in the previous introduction lecture, your synchronous speed will be purely depending upon the frequency. Okay, so here you can infer that. Okay, so synchronous speed as per your frequency and your poles, number of poles. So if the sorry, here the number of poles is 6. Okay, so because the total number you have to take. Okay, not the pole pairs. So 1 2 3 4 5 6. Okay, so here you can see the poles for each hertz, 50 hertz and 60 hertz. Okay, so for we can just apply for your two pole. Okay, your n will be, n sync will be 120 f by p, right? 120 f by p. So the speed first we will be finding for your 50 hertz, 120 into 50 divided by poles is 2, right? So 2. So what happens? This cancelled out and this cancelled out. You will be getting out 30. So 30 into 50, you will be getting 3000. Okay. So similarly for different type of hertz and different types of pole numbers, they have calculated. Okay. So this is what a rotating magnetic field looks like. So we have seen about the stationary magnetic field. So this is what your rotating magnetic field looks like. So you can clearly see each and every phase will be 120 degree apart. So R and B is 120 degree apart. Then R and Y is 120 degree apart. So this is how the principle involves. So here the rotating magnetic field is given by your magnetic field, okay, intensity. So which is nothing but Bm. So the net value will be the summation of all the three phases. So if this Bm is your maximum magnetic field intensity, so sin omega t. So first for your R phase it will be 0 degree. Then again for your B phase it will be 120 degree. Then for your Y phase it will be 240 degree. Okay. So now you have to substitute. If substituting means you will be getting like this. So here they're taking as a vector quantity. So finally, if you are solving out means you will be taking as a vector two dimensional as x vector and y vector. Okay. So this is how it looks like your rotating magnetic field at various degree. So here you can see the variation in your degree. So here as a so this is what looks like the RYB phase. So here this X represents means the magnetic field is getting into. At the same time, O represents means the magnetic field is coming out. Okay, so here if it is X means from O to X it comes out, and similarly the this rotating magnetic field will be formed out. Okay, so this is how it looks like. So you have a clear idea of this. So coming to the principle of operation. So as I said, the rotating magnetic field cuts the rotor windings. So whenever a magnetic field cuts the current carrying conductor, what happens? An EMF will be induced. Okay, so the same principle is involved here. So due to the fact that rotor windings are short circuited for both squirrel cage and wound rotor, an induced current will be flowed. Okay, so in your rotor, what happens is that your windings and your either in squirrel cage or the wound rotor it will be short circuited. So what happens is that there will be a closed loop. There will be a closed loop in the rotor. So this enables the flow of your current I. Okay. The rotor current will also produce another magnetic field. Okay, this rotor current will also produce another magnetic field. Another magnetic field. Okay, so a torque is produced as a result of this two interaction of the two magnetic field. A torque will be produced. So this is what your torque. So here this BR represents your rotor magnetic field, whereas this BS represents your stator magnetic field. Okay, stator magnetic flux density, and this rotor represents your DR represents your rotor magnetic flux densities. So here you can see induction motor speed. About your induction motor speed, at what speed will your induction motor run? Whether can they are able to run at your synchronous speed? So synchronous speed is nothing but your maximum speed at which your induction motor is possible to run. So if the rotor has synchronous speed, which will be same as that of your rotor magnetic field. Okay, so the we have seen about the rotor magnetic field, right? So this is what your rotor magnetic field, which is rotating. So if the rotating magnetic field that is at the rotating magnetic field, there's a possibility for your induction motor to run at your maximum speed, which is nothing but your synchronous speed. Now, then the rotor will appear stationary to the rotating magnetic field, and the rotating magnetic field will not cut the rotor. Okay, that is the rotating magnetic field was caught up by your speed of your induction motor. So if this is a rotor means, and this is your magnetic field means, so if this is rotating at one particular speed, and this is rotating at a particular speed. So at this speed, there's no problem. But when both are rotating at a same speed in the sense, then the rotor will be appear to be in a stationary part. Okay, so it is not possible for an induction motor to run in a synchronous speed. So this is the main theory. So if it is coming at your synchronous speed means what happens? Surely the rotor will be at the stationary part because it has caught up the rotating magnetic field. Okay, so there won't be any kind of electromagnetic inductions. Okay, so no induced current will flow in the rotor and no rotor magnetic flux will be produced. And hence, due to this, if there is no rotor magnetic flux means this value becomes zero, right? So this value becomes zero. So your torque will also become zero. Okay, so this is how it works. When the speed falls, the rotating magnetic field will cut the rotor winding. So always in an induction motor, it is not possible. It is not possible to attain to attain your synchronous speed. Okay. So then, how you can find the induction motor speed? Okay, so this induction motor speed will be always less than the synchronous motor speed, as I have said, and the difference in the two speeds is given as a slip speed. Okay, so it is your slip speed, and speed of the magnetic field is your nm, and mechanical short speed is nothing but cnm. Okay, so speed of the magnetic field is nothing but a synchronous speed. So next is slip value. How we can find? So slip value can be found by this formula: S is equal to n sync synchronous minus nm by n sync. So S is your slip value. So this S value will be varying from 0 to 1. Okay, this is the slip value it takes. So if the rotor runs at the synchronous speed, then your slip will be 0. At the same time, if the rotor is stationary, your slip will be 1. So initially your slip will be 1 because without any supply, your S value will be always 1. The slip will be always expressed in terms of the percentage by multiplying with 100. Now again here comes your difference between your induction motor and your transformer. So here, as I said, the difference between, you can just compare it with the primary and the secondary. So the primary windings produce an second induced voltage in the secondary winding. Similarly, for your induction motor, the voltage applied to the stator produces an induced voltage over your rotor. So this will be acting as primary, means this will be secondary. So your stators compared to your primary and your rotors compared to your secondary. The difference is that in case induction motor, the secondary windings can move. Okay, due to the rotation of the rotor, the induced voltage in it does not have the same frequency of the stator. Okay. Coming to the frequency of the voltage induced in the rotor is given by, so this formula, that is n equal to, we have already see 120 f by p. Okay, so here you need f, right? So keep the f on the side, take to others to the other side. So n into p divided by 120 is equal to your frequency. So this n is nothing but the difference between your synchronous speed and your rotating magnetic field. So that's what here they have given. Okay, so then they have expressed this in terms of your slip value. So if the slip if you are taking means, so fr nothing but the frequency at which the rotor is rotating, or the rotor frequency is equal to s into the supply frequency fe. Okay. So that's what here they are given. So again here they have repeated it, that is if s is equal to 1, the frequency will be, that is your rotor frequency will be similar to that of your supply frequency. At the same time, if the s is equal to 0, the frequency will be 0. Okay, so here it is a torque equation they have given. So omega is equal to 2 pi ns by 60. So this is what your rotating magnetic rotating speed involves. So here your tau load is be equal to, that is your torque will be p out by omega m. So this is what your omega. So tau, your load torque will be equal to your output power by your rotating speed. So next is horsepower. This torque can be uh, made to express in horsepower. Okay, so in your horsepower, if you're dealing with means your watts will be converted into HP. So 1 HP is equal to 746 watts. So we'll be dealing with a small problem. Okay, example problem. At 208 volt they have given. So given is the supply V equal to 208 volt. So speed power is given by 10 HP. So P is 4 pole, F is 16. So full load slip they have given. So S is equal to 5%. So you can take it as 0.05. So if they are taking 0.05 is nothing but 5 divided by 100. Okay. So they asked to find a synchronous speed in sync. At some rotor speed they asked. So Nm, rotor frequency they asked. So Fr. So shaft torque which is something but tau. So these are things what they asked. So solution again guys move on. So N sync is given by 120 F by P. So from this F is 4 pole and frequency is 16. So you'll be getting a speed of 1800 RPM. So next is regarding your speed. Nm is given by 1 minus S into Ns. So here the S value is 0.05. So Ns value you know we have found out. So you have to substitute it. So it will be 1710 RPM you will be getting. Next the rotor frequency is Fr equal to S into Fe. So supply frequency you know, S also you know, so you'll be getting the value of 3 hertz as your rotor frequency. Tau load is nothing but P out by omega m. So but the P out here they are given in your HP. So you have to convert this HP into watts. So 10 HP the conversion is over here. So finally if you are putting out means you'll be getting the value like this. Okay. So this is what with respect to the problem, and the lecture is over. Thank you.